Students, welcome back to this lecture series of M.Sc. Part 1 Physics, Mathematical Methods in Physics. Okay, so in the last class we discussed about the power series and the complex sequence. Okay, so in this lecture we are going to discuss one important theorem, that is Taylor series or the Taylor series theorems. Okay, so this is a theorem of functions f of z that is analytical inside the circle. This equation is given the circle z minus z naught in mode z minus z naught is equal to r. This defines the circle, may be represented inside this circle as a convergent power series. F of z is equal to summations our n is equal to 0 to infinite here. Okay, an into z minus z naught power n. Okay, this is a series, power series, that is analytical in the circle z minus z naught, and this series is convergent. Okay, so and this an, this is a characteristic coefficient of this z minus z naught. So this is defined with the an is equal to 1 by n factorial into f power n, the function of z naught. Okay, so this is a characteristic coefficient. So if you see this proof of these theorems, so first I am consider one region or one domain, that is this. Okay, this is one domain I am considering which is radius or is equal to r of this circle. Okay, you can consider the domain or the circles. Okay, and the center of this domain, that is, or the center of this circle, that is z naught, and radius is a capital R. Okay, and another one circle I am consider inside in these regions, that is this one. Okay, so I am consider one arbitrary points, that is z, and distance from the z naught to z, this is equal to z minus z naught, like that. And this radius of this circle, that is I am consider it is psi. Okay, this is a psi. So this closed loop, if we give the name, that is CR, or the okay, CR, this R is defined the radius of this circle, or like that, or the psi. Okay, and the radius of this domain, that is R. Okay, and this z naught is the center of this both loop or the circle, CR and this circle. Okay, so this f of z, if we expand in this region, in this regions enclosed by this CR, okay, if we expand in these regions, then this series is convergent. Okay, or power series is convergent in these regions. Okay, so let's see this theorems or series, Taylor series, that is converged in this region, that is we consider CR. So from this power series, if I write the proof, if I write the in the psi form of this power series, that is f of z is equal to, or by the Cauchy integral theorems, first I am consider Cauchy integral theorem, or the Cauchy integral formula. Okay, so we know the Cauchy integral formula, that is f of z is equal to 1 by 2 pi iota, or the 2 pi I, closed integral over CR. Okay, here we consider this region, so that's why here is a CR, and this Cauchy integral right in term of the psi. So it is f of f is a function of the psi divided by psi minus z naught, psi minus z naught. Okay, and with respect to variable quantity is psi. Okay, so this is expression I am right from this. Okay, by using the Cauchy integral formula. So we know the Cauchy integral formula, that is f of z is equal to 1 by 2 pi iota f of z, okay, z minus z naught dz. Okay, so from this I can write like this expression, okay, for this case. Okay. And for the nth derivative also we know the formula for Cauchy integral formula for the nth derivative. So a power n z, this is z naught. Okay, so 1 by 2 pi, sorry, n factorial divided by 2 pi iota, or a closed integral over c, or here we consider CR, okay, this thing. So it is f of z divided by bracket z minus z naught n plus 1 dz. Okay, so this is Cauchy integral for the nth derivatives, and this is Cauchy integral formula. Okay, so by using these two formula we can modify this mathematical expression for the Taylor series. Okay, so this f of z is analytical in these regions when we consider this psi1 minus z naught. Okay, and this distance is or this, if you compare this z minus z naught, so it is always less than the psi minus z naught. Okay, like this. So this point is also interior in this region. Okay, so if we expand this series into this region, so it is convergence. Okay, so here I am consider this denominator terms, that is 1 divided by psi minus z naught. Okay, so okay, it is z. Okay, you can consider z naught. Okay, so psi minus z naught I am considering. So this expressions we can write like this: if we divide and subtract, add and subtract one quantity, that is z, so it can be 1 by psi minus z minus z naught plus z. Okay, just adding this minus z and plus z. Okay, so this is equal to if I write 1 divided by psi minus z minus z naught minus z. Okay, z naught. So these things here is z naught. Okay, z naught minus z. Okay, so this is 1 by psi minus z minus z naught minus z1. So these expressions, if I write again like this, if we take out the common, that is 1 by psi minus z. Okay, so this is like this: 1 is equal to 1 divided by psi 1 minus z, that is we take out the commons, into, so here 1 minus this thing is what 1 divided by, okay, so 1 divided by this z naught minus z divided by psi 1 minus z. Okay, this thing. So this bracket we can write 1 divided by psi 1 minus z is equal to, is into 1 minus this, you can write the z naught minus z divided by psi1 minus z, okay, in the power minus 1 of this bracket. Okay, here is a 1, and here if we write like this, so here is a minus 1. So now this bracket, if I expanding by binomial theorem or the binomial series, then we get like this expressions. If we expand, it is equal to 1 by psi minus z into 1 plus, by the binomial theorems we can write 1 plus z naught minus z divided by psi minus z plus z naught minus z bracket square divided by psi1 minus z bracket square, and fourth terms, that is z naught minus z divided by psi1 minus z all cubes, okay, and the plus, so on we can find out like this. So here for the n terms we can write, for the n terms, that is z naught minus z power n divided by psi1 minus z power n, okay, and here is also other terms, that is n plus 1, n plus 2, like that, okay, and that terms you can call that is a remainder terms. If I write, here is the other term, that is z naught minus z power n plus 1 divided by psi minus z is n plus 1, okay, and so on. Okay, so these terms, that is we can call this after the nth, that is remainder terms. Okay, so here just I am taking, this is R remainder terms. Okay, so this is a series, that is what we consider is equal to 1 by psi minus z, psi minus z naught, that we consider. So psi minus z naught is equal to these things. Now in the previous we consider this one formula, that is f of z is equal to 1 by 2 pi I, by using the Cauchy integral formula and the closed integral over CR, f of psi divided by psi minus z naught and those side. Okay, this is expressions by using the Cauchy integral formula we consider this mathematical expressions. Okay, and this denominator terms, that is 1 by psi1 minus z naught is this thing. Okay, so if I put these expressions into these equations, then it is like this. Okay. Now f of z is equal to 1 by 2 pi eta close integral over CR, this f of psi1 as it is, and divided by psi minus z naught. See, these things I am substituted here. If before that I multiply to all brackets, okay, so this if I multiply to psi minus z naught to psi minus, this is 1 by psi minus z. Okay, see, if I multiply, so this become like this, 1 divided by psi minus z plus, here is a square, here is cube, here is a power 4, and here is a n plus 1. Okay, so now these things I put into this equation. So it is closed integral over CR, and this f of psi divided by now for here is the numbers of terms. Okay, so we consider one by one. So first term, if I put, so that is 1 by psi 1 minus z, okay, into this equation. So it is psi minus z, okay, for the first term, and from these things is multiplied, so that is dou or dou xi. Okay, so this is first for these terms. These expressions I write for this expression I write for these terms. Okay, now for the second terms, so it is plus 1 by 2 pi eta plus close integral over CR and f of psi 1 divided by psi 1, sorry, now for this expression psi 1 minus psi naught. Okay, so for the second term I write this z naught minus z divided by psi 1 minus z, power is 2 or the square. Okay, so here this term, that is z naught minus z divided by psi 1 minus z power is 2 or the square, okay, and into psi. Okay, now similarly if I write for third terms, that is z naught minus z whole square, so it is like this, and here is 1 factorials, it is 1 factorial, here is 2 factorials. Okay, so let me clear this first, and then we consider here factors. Okay, so here 1 by 2 pi eta close CR f of psi 1 z naught minus z square divided by psi 1 minus z cube and this side and so on. Okay, so if we put like this this all terms, that is for the power 3 and for power nth, so we get the nth derivative of the Cauchy integral formula. Okay, so expressions for the nth derivative of the Cauchy integral formula. So we know the Cauchy integral formula, that is f power n z is equal to 1 by n factorial divided by 2 pi eta close C f of z divided by z minus z naught or n plus 1 dz. Okay, so this is a Cauchy integral formula. So if you observe these things, so it is Cauchy integral formula only, and these things if you observe, so it is a Cauchy integral formula for the second or the first derivatives. Okay, so one expression I already write, that is a n is equal to 1 by n factorial f n z naught. Okay, for the, so from this we can write this f of z is equal to n factorial by n. Okay, so f n z is equal to n factorial into n, like this. Okay, so let's check. Okay, so if I put for these things here, so this is n factorial by n, and this z naught minus z naught, this is okay, I am right here. Okay, so if I write f of z is equal to this is f of z okay, f of z and plus for this expression, that is I think this is f of z naught. Okay, so f of z plus, and for the second terms we can write if we take out this common, that is z naught minus z, because this is independent on this side. Okay, so this factor I am take out the commons, so it is z0 minus z, and other things, that is nothing but the f of z. Okay, similar things. And here is one, that is, if for the second derivative we can write, here is a n divided by the n factors. Okay, from here 1 by n factor, so f n z naught. So here I write f prime z, this f prime z for the derivative of this Cauchy integral or these functions, first derivative of these functions. Okay, and divide by n is equal to 1, so it is 1 factors. Okay, and the plus for these terms we can write z0 minus z square. Okay, these things is a take out commons, and other thing is a same it is, so it is f double prime z divided by 2 factors, but here is a n is equal to 2. Okay, or the second derivative of these functions like this. If I write for the next term, that is z0 minus z power 3 f triple primes z divided by 3 factors. Okay, and like this we can write for the n terms, that is z0 minus z power n f n z divided by n factors. Okay, so this is expressions. This expression is called Taylor series. Okay, so we can solve this by using this Cauchy integral formula, or the Cauchy integral formula for the nth derivatives. So this expression is called the Taylor series. And now this f of z, this is a series that we expand in the regions R. Okay, that what I draw the diagram in the last topics. Okay, so in that regions, this f of z, if we expand, so this function is analytical, and if it is analytical, then it converges in these regions, or what we consider the regions. Okay, so this is about the Taylor series. Now one more concept, that is if related to this Taylor series, that is Mclaren series. And this Mclaren series, if we consider z is equal to 0, or z0 is equal to, z is equal to 0. Okay, z is equal to 0, so this summations over an z minus, here for power series I am considered z minus z0 power n. Okay, this thing. So if this z0 is equal to 0, then the summation an z power n, this things is called the Mclaren series. Okay, so at this z is equal to 0, or the center is equal to 0. Okay, sorry, center is equal to 0 means radius is equal to 0, so an z power n is equal this series is called the Mclaren series. Or also this is a series, it is z power n. Okay, so this is about the Taylor series. Okay, let's stop here. We conclude this lecture here.